Good day, students. Welcome to our second online session for the course Computer Organization to the course code 33343. And this session is for BEE7A students. And in this session, we will be continuing our lecture which we have discussed in the previous session for the computer abstractions and technologies. So to start with, let us first see the content which we will be covering in today's session. Basically, we have left our discussion in the previous session for defining the performance, and we haven't discussed that in detail. So in today's session, we will be discussing the performance parameters, for example, the components like response time and throughput, and how to measure the execution time or response time. We're going to discuss that in detail with some practical examples, and then last but not the least, we will discuss the power trends in the computer systems. So to start with our discussion, let us first review the contents which we have studied in our previous session. In our previous session, we have defined the computer organization and computer architecture, and we've seen that computer organization is basically the microarchitecture or the part of the computer architecture that basically deals with organizational structure of the computer system in order to implement a particular instruction set architecture. Afterwards, we've defined the program flow and the level of the program from the high level till machine code, how our program is being basically converted or mapped to the hardware. We've discussed that in detail. That was the main point of concern in our previous class. And so to start our today's session, this is also the chapter number 1 of the book Computer Organization and Design, a hardware software interface. Uh, we can also study the same content from Computer Architecture, the Quantitative Approach book from the same authors, and the slides and the content basically are taken from MK publishers. Uh, so we're going to acknowledge them for all the content. So student, how we're going to define performance? Basically, let us see with the example of the airplane, and we've got the series of airplanes and how we're going to define the performance and what are the parameters. If you consider that, and we can say that the performance is better. So for example, we can have different parameters in order to define the performance. For example, we can have the passenger capacity of the plane, and the plane with more passenger capacity has higher performance as compared to the other. For example, if we consider this metric to evaluate the performance or to judge the system. The second is the cruising range in miles, and definitely the plane with higher cruising range for specific distance or in terms of miles has better performance as compared to the others. That can also be a performance metric. The third is the speed, that is the cruising speed, and definitely the plane with the higher speed is efficient as compared to the other plane if we are considering this as a performance metric. And then we have the passengers with miles per we can say the cruising speed comparison. So we have different performance matrices, and if we consider those performance matrices, we can say that the performance of the planes can vary depending upon that particular performance metric. For example, for the passenger capacity, we can say that Boeing 747 is efficient as compared to the others. For cruising range, we have the Douglas DC is efficient as compared to the others, and similar for the other two parameters. So performance is a relative term basically that depends upon the parameter which we have selected in order to evaluate the systems. So depending upon the performance metric, we basically compare the systems, and that gives us result with that particular metric. And it is not necessary that in one performance metric, if the system is performing well, and in the other performance matrices also the system will be performing well. We can see that example of this Boeing 747 here. So we can say that performance with respect to passenger capacity of Boeing 747 is efficient, but if we compare the cruising speed, it's not efficient as compared to the other systems. So the overall performance basically depends upon all these factors, and we have sometimes the trade-off between the performance parameters, and we have to have a system or a standard in order to compare the systems in order to evaluate the performance. So same concept is applied on a computer system as well. We have some different performance parameters or matrices that are used to evaluate the system performance while comparing within a system, or we can compare the system with some other systems. So we have to see those performance matrices or the parameters or the factors that basically affects the system performance. So we've got two important parameters on a metric that basically defines our performance, and basically we have a response time of the system, and response time basically the system that when we have initiated the task and how long the system has taken to complete or to accomplish that task. That is basically the response time, and we can also call it the execution time, the CPU time, or the wall clock time. So the response time is when we have assigned the task to the system and when that task is completed or executed. That is basically the response time. The second parameter is the throughput. Basically throughput depends upon the total number of work for a specific time frame. That is the throughput. And definitely if we are using the throughput as a performance metric, then the system with higher number of tasks per specific time is much more efficient as compared to the system with lower number of tasks per unit time frame. So the throughput basically tells us the total work done per unit time. For example, the task transaction for specific time frame, in this example per hour. As far as the response time is concerned, the system with the lower time response time is much efficient as the system taking more time to complete the task. For example, we have assigned a task that completes on a particular system in, for example, 3 seconds, and the same task is being performed by a system on 5 seconds. Then definitely with respect to the response time of the system that completed that task in 3 seconds is much more efficient as compared to the system that has completed in 5 seconds. So this is the definition of the response time and the throughput. Now I float a question to you, that how the response time and throughput are affected basically by if we replace a processor in a system with a faster version. So do we get the performance improvement with respect to response time or the throughput? Or the second option is, if we add more number of processors, then what would be the effect of using more number of processors on the response time and throughput? So I want to hear your comments on this particular thought. So basically in this course we will be focusing on the response time. Our primary piece of concern, we can say that the point of concern is basically the response time within a system, or if we are comparing two or more different systems, then this is the performance metrics which we will use in order to evaluate our system performance. Now we've said that performance is relative, and performance, if you define the performance, that is basically with respect to response time, that is basically the inverse of the response time or the execution time. Lesser the execution time is, better the performance is, as compared to the example which we have discussed earlier. And we have also the example in order to define the performance. So performance is basically 1 over the execution time. Execution time is basically the response time of the system. And we can say that x is n time faster than y. If we claim that the system x is n times, n is a metric that defines that this system is how much faster from the other system. So what we are doing, that we are comparing the performance of the x system with the performance of the y system. So performance of x divided by performance of y. So in terms of execution time, if we say that performance is equal to 1 over execution time, we can say that execution time of y divided by execution time of x equals n. So we can say that if n equals to 1, that means that both execution times are equal and there is no performance difference between the two systems. And if n is greater than 1, then in that particular case the x system has improved performance as compared to the y system by the factor of n, or n times, we can say that. And we can discuss this with an example. For example, if we run a program on two systems, on system A and system B, and the execution time of completing that program on system A is 10 seconds, and on system B it's 15 seconds. So we can clearly say that A is much efficient as compared to B in terms of response time or execution time. But how much A is efficient with respect to B? So we have to compute the relative performance. So relative performance of A divided by performance of B, this is basically equals to performance of A divided by performance of B, which is equal to, if we take the reciprocal of the execution time, so that is equal to execution time of B divided by execution time of, or the response time of A. So in that particular example, in our particular case, 15 second divided by 10 second equals 1.5. So we can say that A is 1.5 times faster as compared to B in terms of execution time for the same program. Now, how to measure the execution time? Basically, what are the factors that basically affects our execution time? That basically depends upon the elapsed time at the CPU time. Basically, the elapsed time is basically the total response time, including all aspects. For example, the processing, the I/O, the OS overhead, the idle time. Basically, that determines our system performance. And the CPU time basically is the time spent processing a given job, basically by the processor itself. So we don't have to consider the I/O time in that processing time. Other job shares are not included in that. So basically, CPU time basically comprises of the two time, that is the CPU time, system CPU time, and the user CPU time. The system CPU time is the time that is being utilized in order to process the system utilities or the system application or system software. For example, the operating system time, and the user CPU time is actually the core programming time or the program time that is being used in order to execute that particular program on a system, or by the processor, by a specific processor. So different programs are affected differently by CPU and system performance basically. So let us see how we're going to measure the CPU time. But first of all, let us have the idea of the CPU clocking. The clock source that is being used in order to provide the clocking to the sequential mechanism that has been involved in the processor design itself. So processor design contains some combinational modules as well as some sequential modules. So all those sequential modules that do retain some clocking information in order to operate, they require a CPU clocking mechanism. And for example, for a particular processor or a particular digital hardware that has a constant clock rate, for example, we say that a processor with 3 gigahertz clock, that means that its internal circuit is operated with a clock frequency of 3 gigahertz. So if we consider the clock period, these are basically the number of cycles. So clock pulses are basically the periodic train of pulses, digital pulses, and one clock period represents one high pulse. This is one high pulse and this is one low pulse. So in order to determine the time frame of that, we take the reciprocal of the frequency, that is equal to T is equal to 1 over F. So that gives us the time frame or the clock period, or we can say that clock cycle time also, or the CPU time also, that is affected by the factor of the clock period as well. So either we can represent that with respect to the clock period, that is the duration of the clock cycle, or we can have a rate, that is the clock frequency, that are the cycles per second. So these are the two examples that represents the clock period and the clock frequency. So the CPU time is being computed. This is basically the user CPU time that is being computed by the number of CPU cycles, CPU clock cycles that are consumed in order to process that task. 15, 20, 30, 100,000, how many cycles of the CPU are consumed in order to process that program or in order to execute that program, and what is the clock cycle time. We basically take the product of both of the terms to determine CPU time. So in terms of clock rate, that formula is CPU clock cycles divided by clock rate, since clock cycle time is reciprocal of the clock rate. So what are the factors that basically tells in this equation that the performance is increased basically? So if we can reduce the number of clock cycles in order to complete that program to process, we can say that our performance is improved. The CPU time is reduced, and when CPU time is reduced, the performance is basically the reciprocal of the CPU time or the response time or execution time. So performance will automatically increase. Or we can say that if we can increase the clock rate, by increasing the clock rate, if you see that the clock rate, basically CPU cycles divided by clock rate, or the clock rate has a reciprocal relationship with the clock cycle time. So if we increase the clock rate, definitely the CPU time will decrease. So in that particular case, the performance will automatically increase. So if we increase this factor that is in denominator of this equation, automatically the CPU time will decrease and performance will automatically increase. Or we can say that the hardware designer do have some trade-off clock rate against cycle count. So there is no free hand that we can increase the clock rate by a certain proportion or infinitely. So we have to observe those trade-offs and the hardware constraints as well. Now, considering the CPU time example to compare the system, for example, consider the following parameters. We have a computer A that has a 2 GHz clock and 10 cycle CPU time, and a designer want to implement or construct computer B that will run the same program which is taking 10 seconds here on computer A into 6 seconds. So we want to implement a computer that will basically implement the same program or execute the same program in 6 seconds rather than executing the program in 10 seconds. But there is a constraint. The designer has determined that we can increase the clock rate, but if we increase the clock rate, the number of cycles are also increased by this factor. So this is the constraint. So we have to tell the designer that how much faster the computer B clock should be, so that that program that is taking 10 seconds to complete on computer A should take 6 seconds to complete on computer B. So first of all, if we can determine the clock rate B, we can determine the clock cycles of computer system A, and we can see that the clock cycles of the computer system A has an effect of 1.2 times. Basically that is being multiplied with the clock cycles for the computer B. So if we put the values in our expression, basically we can say that the clock rate is basically equals to 4 GHz in order to run the same program from 10 seconds to 6 seconds. Now you can see that we have doubled the clock rate, but it does not guaranteed us that our execution time is also being reduced by 50% or half. So basically here we are consuming the clock, we are computing the clock rate of B, and for the clock rate of B we require the clock rate of A, and for the clock rate of A we are using this formula that gives us the clock rate of A, and we have put this value into this formula in order to determine the clock rate of B that is required in this problem. So this is the clock rate B. Now, in this particular example, the CPU cycles were given basically. The relationship of the CPU cycles of the two systems were given. But if we have to compute the CPU cycles, then we have to see the factors that basically affects our CPU cycle basically. So the CPU cycle is being affected with the two factors that are been involved in computation of the CPU cycle. The first factor is the instruction count. In short form, we call it as IC. That are the number of instructions that a program have, the total number of instructions that a program have, that are the instruction count, and cycles per instruction. In a short form, we call it as CPI, that are the average number of cycles that an instruction can take in order to execute. So we can say that the CPU time is equal to instruction count multiplied by CPI divided by clock rate or multiplied by clock cycle time. So the instruction count is basically the number of instructions for a program, and that is determined with instruction set architecture and compiler. The average cycle per instruction basically that are determined by the CPU hardware, and if different instructions have different CPI, then we have to compute the average CPI affected by the instruction mix. Now coming to the example, we've got the two systems in this particular example. The first is computer A, the second is computer B. The cycle time of computer A is given, that is 250 picosecond. The cycle time of computer B is also given, that is 500 picosecond. The CPI of the both system are also given. CPI of computer A is 2 and CPI of computer B is 1.2. And both instructions are having the same instruction set architecture, which means that the program that is being implemented on computer A and computer B will have the same instruction count and same instructions. So we have to compare these two systems, and we have to determine that which computer is faster from other, and by the factor of how much we have to determine that. So for that we have to compute the CPU time of both the computers. So we are plugging in the values for the CPU time for the A, that is equal to instruction code multiplied by CPI into clock cycle time, and similar for the CPU B. And then for the performance of A equals divided by the performance of B equals CPU time of B divided by CPU time of A. This is basically for the relative performance. Performance of A divided by performance of B, which in fact equals to CPU time of B divided by CPU time of A. Just plug in the values and you'll got the factor, and we can say that computer A has 1.2 times better performance as compared to computer B. Or we can say that computer A has 1.2 times enhanced performance as compared to computer B. Now coming to the CPI in more detail, if different instruction classes take different number of cycles, then the clock cycles are computed in by using this representation. And if we have some relative frequency of instructions as well, definitely, and then we'll use the weighted average CPI is computed with this representation. Now coming to another example, so we have to for the CPI basically. So basically we have the alternative compiled code sequence using instructions in classes A, B, and C. The data that has been given here for the class A, B, and C. Instruction class A, B, and C are the three dedicated classes, and CPI for these classes are 1, 2, and 3. And instruction count in sequence 1 is 2, 1, 2. And instruction count in sequence 2 is 4, 1, 4. Basically we've got two sequences, and we have to compare the relative performance here, or we can have to, for the two sequences or more number of sequences, how we're going to compute the average CPI. Basically this example is related to that. For the sequence 1, the instruction count equals 5. Just add those instructions, and for sequence 2 the instruction count is equal to 6. Now the clock cycles, you can say that that is basically the product of this thing added with this thing added with this thing. So 2 multiplied by 1 plus 1 multiplied by 2 plus 2 multiplied by 3 equals 10. Now the average CPI is basically the number of clock cycles divided by the total number of instructions. Basically that is 10 divided by 5 equals, this is the average CPI for that particular architecture. Similarly for sequence 2, with the instruction count we have got 6 and average CPI is equal to 9 divided by 6. So in order to summarize the performance, basically CPU time is dependent upon the instructions, number of instructions we have in a program multiplied by cycles, CPU cycles per instruction, or the average number of cycles we are taking to compute uh, that to execute that particular instruction, and then we have the clock rate or clock cycle time basically. So, and performance basically depends upon the algorithm. Basically that affects our instruction count and possibly the CPI. On a programming language also affects our instruction count and CPI. The compiler also affects our instruction count and CPI, and instruction set architecture definitely affects our instruction count, CPI, and the time basically, that is computational time that is required to compute that particular instruction. So these are the factors that basically can affect our instruction count and possibly the CPI as well. Now coming to the power trends, basically these are the trends that tells us that with the passage of time, with advancement in our technology, what are the power requirements and how we're going to deal with that requirements basically. So if we see that in this particular graph, we've got the different systems here, starting with 8286 till this particular architecture that was introduced in 2007, and similarly this trend will follow on till we can say that 2020 as well. These curves basically follow the same similar kind of pattern for 2020 as well. So if we can see that from this graph here, that effect on the clock rate basically and the power consumption basically, if you can see that there was a dramatic change here, or we can say that more effect here in this particular time frame, and after this particular time frame we don't have any much improvement as compared to the previous one. So we can say that the reduction in power or the utilization of the power and improvement of the clock rate, definitely we have some constraints here and we don't have any free hand here so that we can optimize the power consumption or we can improve the clock rate here. So for the CMOS technology, the power is computed with this forming relationship. Power is equal to, that is basically the dynamic power, that is equal to capacitive load of the system multiplied by the voltage square into frequency basically. So if we increase the frequency here, the power consumption basically is not as much affected with increase in frequency and capacitive load. But if we increase the voltage here or decrease the voltage, that is basically in the terms of square, basically that affects our power consumption as well. So reducing the power basically, what we are doing that, suppose that a new CPU has 85% of the capacitive load of the old CPU as compared to the old CPU, and we've got 15% reduction in voltage and 15% reduction in frequency. So how much with how much factor we can say that the power consumption is reduced here in this particular example. So the new power has been computed as the capacitive load old, and the reduction in old was 15%. That was we are multiplying 0.85 here with the voltage old multiplied by 0.85, since we have also got 15% reduction here, and multiplied by frequency old multiplied by 0.85, also the 15% reduction in the frequency of the old system for the new one, divided by C old into V old square into F old, and by solving this relationship we came to the conclusion of 0.52. So what is the constraint here? That the power wall, that is that we don't have free hand for the voltage reduction here, and voltage is totally dependent upon the implementation technology and how much we can scale down that technology and how much we can reduce the voltage in that particular technology. That is dependent, and what are the difference between the logic levels and how much we can reduce the difference between those two logic levels. That basically depends or affects the reduction in our voltage basically, and we can't remove more heat here. So these are the two challenging factors basically that basically affects our performance basically in terms of power. How else we can improve the performance? We can use the concept of the parallelism, of the instruction level parallelism, and we can improve the memory latency within a system. The response of the memory, if we can improve that, definitely we can improve the performance of the uniprocessor system here. And we can see from this graph here that with the passage of time, and this is for the performance, comparative performance with this particular setup with respect to time here, and we can see that this is the factor that is been constrained by power. We can see that the development in the system was in a much higher pace and system performance was much more improved, but achieving at this level, there is no much improvement as compared to the previous one due to the power constraints and due to other performance factor constraints. This graph will basically continue on till 2020. So in our today's session, basically we have seen the important factors, for example, the response time or the CPU time that basically is used to determine the performance, the relative performance. And if we are comparing the two systems relatively, then we can say that this system is better as compared to the other system. Then we have factors like execution time that basically determines the performance. Similarly, at the same time, we have discussed the power constraints here, and the power factor, basically the system that consumes lesser power and can dissipate lesser heat is much more efficient as compared to the other one. And we have seen that we have some constraints in terms of scaling, in terms of changing the parameters in while computing the power consumption of the particular system. Well, student, that was all for today's session. I hope so you will understand the implementation and the computation of the response time of the CPU time. And if the CPU time is required to determine the performance, then you will be able to compute the performance with regard to the computation of the CPU time.